start, as it was said, you know me quite well, so I would like just to tell you that with the nature-based solution, I'm since, oh my God, since my PhD studies, and I have a opportunity to be chair of IWA scientific group Treatment Wetlands for Water Pollution Control. Now I'm working as a full professor at Gdańsk University of Technology, and I am also a coordinator of so-called Ecotech Center. And for many, many years, I work in global wetland partnership, water partnership, and since 2001, I'm in sustainable sanitary task force for Eastern and Central Europe. And I was wondering how to start today. And first will be the causes of climate change, natural and anthropogenic factors. This is still a kind of doubt which surprising me very much. And I would like to share with you the graph which was released very lately. And as you can see, Poland is the winner, which is, in my perspective, not so good, because as you can see here, the question to the audience, you can find your countries here, and unfortunately, I would say unfortunately for us, because we have Poland, Czech Republic, Hungary, countries which are together with us in KONE project. We are we are three on the top, and the question was set in this way, that climate change is for the most part caused by natural cycles rather than human activity. And if you can see, if people say yes, it means that they think that climate change is mostly caused by natural cycles. So in Poland, it's 52%, in Czech Republic, 51%, and in Hungarian also 51%. So it means the majority of people think in this way, that this is caused by natural cycles, and in this moment they feel not responsible to do anything. I understand that this is clear for you, so we go further with this, and in this moment, from my perspective, it was very important to tell you how actually it is, and how do we know that now majority of societies, different national and world scientists are on the position that this climate change is human-made. So first of all, we need to distinguish between weather and climate. And very simply speaking, the weather is temperature, wind, rain, cloud, atmospheric pressure, and humidity. Actually, this is what we can see, what we can observe through the window. We used to say that this is what we can observe through the window. And of course, weather is influenced by the global climate system. And in majority, we can predict over a smaller region that the weather could be similar. Instead, climate is defined as a long-term weather averages, some kind of variation, extremes, and local climate are influenced by the distance, for example, from equator, elevator, distance from the water bodies, vegetation, present or absence of mountains. We can understand this quite well, and of course other geographical features. Climate also varies over the seasons, years and decades, and much longer time scale, such as, for example, ice ages. And from this perspective, it's very important to understand that, for example, some cold weather is not a climate. From this perspective, is very important to understand. And what is even more complicated, and I will ask you if somebody do not understand something and want me to repeat, please don't hesitate to ask. So it's very important to understand that the Earth climate system is something more than the weather which we can observe through the window or when we are in open space. So the Earth climate is a very complicated system which consists of two interacting together system, like for example atmosphere. Atmosphere is a very thin layer of gas surrounding the Earth, and this atmosphere, as you can see here, play very important role in our climate system. Then we have the lithosphere, and this is the land surface such as soil and rocks, and also human-made surface such roads and buildings. And I was reading that now we have more concrete than natural soil. So it means that we change a lot this lithosphere. And of course, this causes some consequences. Then we have the hydrosphere, the earth liquid water in ocean, rivers, lakes, and also underground. Then we have the cryosphere, the frozen water in ice and snow, and very important, the biosphere, the living things such as plants and animals, including humans. As I told you, we as a human, we introduce into this climate system, which is complicated, and there is a lot of reaction between these different five systems. They are interacting. They are, for example, releasing some carbon. They are taking some carbon from the atmosphere, which is very important. And I hope that we can today observe, you can understand how it works. So this is very important. And here arises the question: if human, when we can say that we are from 50 to 100 kilos by average, can we change the Earth climate system? And here there are some data for you to understand from the previous what means biosphere, and data given by American Science Academy for 2023. Sorry for this mistake, doubles the year. We need to understand that mass number of mammals, wild mammals living on the land is only 20 million tons. In water, we have wild mammals around 40 million tons. But people altogether consist of 390 million tons by weight. And livestock, which we really grow for our needs, is even double as people. So in this moment, we can understand how big interaction on our land, on our Earth climate, we as a human really put on our Earth. Then we need to understand such two mechanisms. With the term climate change, it refers to the Earth climate changes over the time. So it means usually caused by long-term natural processes, such, for example, like changes in Earth orbit. I will come back to this. But first of all, we need to understand that we have two different mechanisms. First one is the feedback mechanism, which are climate-affected phenomena occurring within the climate system as a result of forcing. So if the forcing occurs, then we have the feedback. So this is very important. And the question arises from which we could have the forcing and how feedback we could have. And here you have some information about this. What is forcing? Forcings usually is external influence on our climate system that origin from outside. It means that, for example, if the forcing will be the kind of disaster, cosmic disaster, something like that. It will be the forcing. So, and we know from our history, let's say, very long history of life on the Earth, and we know that we have such astronomical factors, such as a variation of solar activity or change in Earth orbit. Many of you probably have heard about these Milankovitch orbital cycles, which every 41,000 years change the position of the Earth according to the Sun. And this is very important to understand that they are very long-term climate changes. And due to these astronomical factors, we have glacial ice on our Earth. So this is very, very, very important. Then a lot of people say that we have volcanic activity, which can lead to temporary, unfortunately, cooling due to aerosol emission. And that's why I prepared for you these slides, which was really, really a very huge eruption by the volcano Tambora in Indonesia region. And this eruption, as you can see, was many, many years ago. And then people say that there is a year without a summer, because during the eruption we have a lot of aerosols, and these eruptions caused climate anomalies, not change, climate anomalies, which reduce temperature or air by approximately 3 to 4 degrees. And also these anomalies caused that a lot of people starving, and it caused a lot of deaths, even in France, Spain, Switzerland, Belgium, England. And this later on, it was assumed that it was a factor which actually started some political changes in Europe. So as you can see, this theory that volcanic activity caused the climate change because the volcanic released a lot of carbon dioxide actually has no proof, no evidence according to this, what we already know. And also on this list, as you can see, we have these anthropogenic factors, including changes in atmospheric greenhouse concentration, as well as those aerosols which actually are released during the combustion of fossil fuels. And when these factors occurs, then we can expect some further feedback which could alert the energy balance and other phenomena. So about the feedback, the most evident feedback mechanisms include, for example, changes in the intensity of evapotranspiration or extent of sea ice due to the force increase or decrease in atmospheric and oceanic temperature. So we understand that we have, for example, melting of ice, or we have higher evapotranspiration due to a higher temperature. Changes in this evapotranspiration rate influence the intensity of greenhouse effect. And how it happens? It happens because we have different albedo. And here I need to put stress on this albedo because it's very important to understand, to remind from our primary school what actually is the albedo. And here you have some graphs telling us this story about the albedo. So, for example, we have here from Norwegian Polar Institute, we have here the albedo on the land. As you can see, if the land is white, like here, or solar radiation is actually reflected back to the atmosphere. If we have dark cover, then majority is kept on the land and increase the temperature of the land. And this albedo is very, very important for living on Earth. As you can see here, different planets have different albedo. It's not so direct as we can think. It's a bit more complicated. But as a human beings, we, for example, change the albedo. We change the albedo. As you can see, human skin has a very low albedo. It means that we reflect a lot. Ocean has even less. Ocean has even the less albedo. It means that it collects, and fresh snow has a very high albedo. And these are the consequences of our activities, that if due to our activity the snow is melting and there is no snow, our planet achieve more energy. And this is a feedback. This is a kind of feedback due to the change of the albedo of the Earth. And for example, we could have also, this was a positive, unfortunately, and we could have, for example, negative climate feedback, which occurs very, very rarely. And for example, it's a response within the climate system that counteract the effect of initial forcing. This is the negative climate feedback. And we can, for example, imagine, but it's not unfortunately happened, that that negative feedback is when our Earth, our planet, could increase the heat radiation, which following the rise in the temperature. This, of course, could help us to slow down further warming and help to stabilize system. But as I mentioned, it doesn't really. We do not can find any examples of this now. And in some cases, the same phenomena could act either as a forcing or feedback, depending on the origin. And maybe it's a kind of tricky thing that we should understand. That, for example, an increase in atmospheric carbon dioxide levels can be a forcing if it's a result from human activities, such as fossil fuels combustions, since with this phenomena, it's connected another very important phenomena, which is connected to so-called slow carbon cycle. Because if we dig fossil fuels, which were, collected million years ago, stored by our Earth to protect our climate. Actually, it was done, I would say, if we can say that the climate system is clever or wise, we can say that it was a kind of feedback, negative feedback, that it was collected the carbon and stored under the ground, and this was a kind of Earth defense against climate change. So in this moment, this is a forcing. If we, as a human, by our activity, we burn fossil fuel, we release carbon dioxide to the atmosphere. And it could be a feedback if it results from the processes such vegetation dieback or oceanic degreasing, triggering by priority global temperature increase. So depending on the origin, it could be forcing on or feedback. But maybe it's too much for you in this moment. I could understand this. So let's go further with our basic information. Very important is to understand that there is a term of tipping point, and it means that there is a threshold value of specific parameter beyond which the equilibrium state of the climate system shifted inversely. And this is very important information, that to some extent we are not able to predict what happens, and the changes will be irreversible. And example of this feedback and tipping point you can find here. And for example, as I already mentioned, with the albedo, this Arctic sea ice melting, its positive feedback mechanism. Rising temperature reduce ice cover, which lower the albedo and leading to greater solar absorption and further warming. If ice cover decrease beyond certain threshold, this effect alone could drive the complete melting of remaining ice. So in this moment, it will be reversible. Similar situation is this with the permafrost. Probably you have heard that we have a lot of organic matter which was frozen, and in the north part, especially in Russia, and if the permafrost melt, then we will release a lot of methane and also carbon dioxide, which are both potent of greenhouse gas effect, and this process could accelerate the climate change. Very important, and there is a huge discussion about this climate change impact on methane hydrates, which are called clathrates. This is also quite tricky, because methane clathrates are generated in not so deep water, usually in water, about 200 deep sea, very cold water and under pressure. And changing the climate which we have now caused that a lot of this region, when these methane clathrates are generated, now become warmer, and this means that these clathrates become unstable, and this could release the methane which is in this clatrate, and this is also the feedback which could accelerate the changes. And this was the part which we discussed, during which we discussed some basic information. I can understand that part of them are very difficult for you, because this is a kind of I would say physics of atmospheric geological part, which is not so well known by majority of us. But here I would like to draw your attention on the changes of carbon dioxide within, as you can see, many years before, in the so-called geological time scale, which is very important to understand that never in our history, never before, we have so high concentration of carbon dioxide as we have now. As you can see here, we can observe some changes, of course, and within these changes we can observe the temperature on Earth and the condition of living. Somewhere here we have these very huge animals, dinosaurs, and so on. But never in our history the concentration of carbon dioxide was so high. Here you have the time 70 years ago, when we start to observe the rise of carbon dioxide. And here, this is by NASA, and this temperature difference within, as you can see, again, 150 years, let's say, more or less. This is in Fahrenheit, but you can observe here how much the temperature has changed in the north part, especially in north part of our Earth, and this is of course quite sad, I would say, that the temperature has changed so much. And why it happens? As you can see here, this is emission of carbon dioxide by different sectors. This is also by American agency. This is for the year 2003, and we have here total emission of carbon dioxide, and by different sectors. As you can see, you don't need to remind this data. This is just to tell you the story. Also here, global greenhouse gas emissions by different sectors from the previous year, because you can see here for 2016, and we have less than 50,000. This is maybe important. A few years later, we have 8 gigatons of carbon dioxide more. So we release more and more and more by let's say every year. Which has, of course, some consequences. And here, once again, a bit more information about some background. This is very important to understand that on our Earth we have a slow carbon cycle, which means geological cycles, which involves carbon exchange processes that operate on geological time scaling, for example, spanning for thousands on hundreds of thousand years. And this is very important because during this time we have this formation of fossil fuels, and we have fast carbon cycles, which accompanies carbon exchange processes which occurring in shorter time scale, 1 year or decades. And here you have a very nice graph which can tell you that this here is so that it's very slow over 100 years, but actually it's not so slow when we compare to geological scale. This is let's say I would say a human these are let's say human time scale carbon cycles. So we have very slow, fast within 10 years, as you can see here. And we have very, very fast, which is less than 1 year. This is very important because this is the plant growth and decay, which happens, for example, when we have the agriculture, intensive use of agriculture. When, for example, we have carbon release from, for example, from the fire. It's let's say this carbon, which is let's say more or less slow, because usually then after the fire we have growth of the forest again. So this is something like that. Okay, and for example here, this is my more or less the time when I was born. And as you can see here, during this time, we release around a bit more than 3 million tons of carbon dioxide. And we are more or less here. And as you can see, we release much more. We burn much more, and we release much more of carbon dioxide. So this number showing us how much of carbon dioxide we are releasing to the atmosphere, and what are the consequences. As you can see here, on this graph, we have years, and more or less they are from the beginning of this industrial revolution, as you can see, to the industrial revolution, and actually I would say to the end of during the Second World War, where we have this huge consumption of carbon. We start to burn fossil fuels to produce weapons, to produce tanks and other stuff which we need to for the war. And after the release of the carbon dioxide, and then the temperature deviation start. And what is important, it's important to notice that these are different measurement, I would say measurement station from different, we can have some information from United States, from Europe, as you can see, from the different sources, we achieve very, very similar data. And in this moment, we are not able to decline that this is something that one person say, one institution. No, we observe this on each measurement station all over the world. And here I would like to come back to this intergovernmental panel on climate change. And part of this data, which will be presented to you now, is taken from the climate fresk, which was elaborated by a French guy, to teach people how it happens that we have the climate change now, and it was prepared by this guy named Cedric Ringenbach. It was prepared by on the basis of Intergovernmental Panel on Climate Change reports, which are released since 1988. There was 7 such reports released, and based on this, he prepared such kind of climate fresk, which lead us through from the very beginning, from the forcing, from the feedback, and to the consequence of this, what happens. And again, simply speaking, you can see here on this graph the emission of fossil fuels. Here we have the year, let's start from the 20th century, and these lines show us measurement data, actually what happens in the atmosphere, because we can measure how much we can emit of the carbon dioxide, and these are the prediction, these are the models which are made by scientists to predict what happened depending on which pathways. This is SSP, means socio-economic pathways, which shared socio-economic pathways, which we select as a human being for our future. And this blue one, as you can see here, this is the socio-economic pathways. If we follow this what we promised during the Paris when it was in 2015, there was signed by a lot of nationalities. They was signed that we follow these socio-economic pathways, which will be sustainable pathways, and then we can decrease emission. We can decrease emission. This is very important to understand that we decrease emission, but carbon dioxide in the atmosphere stays with us. It means that we decrease emission. We will not release more with these 2 socio-economic pathways, as you can see. This one we are not able to achieve because of many circumstances, like COVID, like war now, and this is something which we are not able to achieve. Maybe this one is possible. And please look at this one in this report. This socio-economic pathways is called road to hell, highway to hell, because on this pathway we are going to dig and incinerate everything what we have on our earth, every fossil fuels. So citation after the Trump dig, drill baby drill. So this is more or less these pathways, and please remember this. You will see what happens with our Earth if we follow these pathways. And again, emission of carbon dioxide. We have now on Earth two major sources of this emission. The first one is fossil fuels, and again here we have the years and we have the peak of this emission, and here is deforestation. It's very important to understand within this very fast carbon cycle that deforestation also contributes to the emission of carbon dioxide, because we usually deforestate because we would like to have the growth of plants for our needs, for needs to grow animals, or for our needs. So we deforestate this a bit longer carbon sequestration, and then we usually burn the forest, and then we plant our plants, which are in a very, very short carbon cycle, which cause that we release more and more carbon dioxide. And is it clear in this moment? Maybe I should ask, is it clear for you what we are discussing, what we are talking about? Can I have some feedback?
Yes, it is.
Yes, it is. Okay. In this moment, I would like you to understand that we have so-called natural greenhouse gas effect and human enhanced, or could be called additional greenhouse gas effect. So, being absolutely frankly, thanks to natural greenhouse effect, we have life on Earth in such, I would say, in such as we know. Without this natural greenhouse effect, we would have life like on Mars, or on means not no life. So it's very important to understand that thanks to these greenhouse gases, which was actually released from lithosphere, we achieve solar radiation, and part of this heat escape into the space. But thanks to this, that we have these greenhouse gases, part of this solar radiation stay with us as a warm, and this caused that on our Earth it was possible to have the temperature without this natural greenhouse gas effect. We will have the temperature around minus 18 degrees. So it will be, as you can understand, very difficult for the life which we know now to grow. I think it would be even impossible for human beings to appear on the Earth's surface if we will have minus 18 degrees. So this is very important to understand that natural greenhouse gas effect is very good for us. And as I show you in this slide, through the years, to the ages, that there is no so high carbon dioxide as we have now in the atmosphere. So what happens? This is very difficult sometimes to understand, that if we release carbon dioxide and methane and other gases, because we have more gases than carbon dioxide. We used to recalculate this greenhouse gas effect into the carbon dioxide as a kind of measurement. These gases are not escape into the space. They are stay with us in the atmosphere. So it means that through the years, the concentration of these gases rise, and we can observe this. And it means that less heat which we get from the sun, this as a solar radiation, stays with us. More remain heat is with us. And here we have now an average temperature. It was around 15 Celsius degrees, more or less, as an average. So this is like that we have, and now an extra cover on our Earth, and that's why we used to say that this is additional greenhouse gas effect or human enhanced greenhouse gas effect. And just to realize to you that this small change in the temperature could cause a very big change for all biota, for the whole climate. As you can see here, this is the last glacial ice, the last when we have here we have Poland, as you can see, and the temperature as average on the Earth was then only 5 Celsius degrees less than we have now, and the glacial melted through 20,000 years. 20,000 years within the temperature less only 5 Celsius degrees. So you can both on the based on this you can imagine that, for example, the temperature rise around 1.5 Celsius degrees, which we observed now last year, show us that the temperature was on average 1.5 Celsius degrees on average higher than usual. So you can see how big changes could be, which actually we are a bit not able to predict. And coming back to this shared socioeconomic pathways, as I mentioned, we now have this plus 1.2 Celsius degrees. And in this, when we burn everything what we have, a highway to hell, we will have the temperature higher 5 Celsius than we have in the previous temperature, which we used to say that it was, for example, in the year 2000 or 2015. So as you can see, this could cause a big change, which is actually unpredictable. These graphs show you that this is something which we are not able to predict how our life on Earth will look like if the temperature rise, for example, up to 5 degrees. And here we have different scenario modeled by scientists, and as you can see here, we again start from this what was in the industrial age, before industrial age, and we keep quite well with this, but suddenly we rise to this 515 parts per million, and here you have the pathways what could happen, and here we have this worst scenario, as you can see, in which it is predicted that the concentration of carbon dioxide will be as double as now, which is actually very difficult to imagine what could happen. And in this moment, very important is to understand how it really works, what happens with the carbon dioxide which is in atmosphere. And here you have the diagram, how it is circulate, more or less, how it is circulate on our Earth. But I would like you to draw your attention here, because this is very important to understand where the carbon, where are the places for the carbon. So where carbon sinks, so-called. Very important is to understand that half of the emission stays in the atmosphere. This stays in the atmosphere, and it means that we are not reflecting so much energy as we should reflect as an Earth. Yeah, for our planet is not reflecting so much energy as it should reflect. 1/4 goes to the ocean, and 1/4 goes for the photosynthesis. But photosynthesis in a very short cycle. It means that every year we produce and we decay in different way. Yeah, of course, depending on if we produce the food for us or for animals. It's even worse if we produce food for animals, because they are producing methane, which is even more stronger greenhouse gas than carbon dioxide. Methane is 24 times stronger than carbon dioxide. So looking for these graphs, keep in mind that majority stays in atmosphere, 1/4 goes to ocean, and 1/4 for this photosynthesis. And as you can see here, these two diagrams we can put together, and this gives us the information what happens with the emission of carbon dioxide and what are the sinks of carbon dioxide. These graphs are, as you can see, comparative, and we can observe this, what happens with the carbon dioxide. This is very important to understand how the climate change actually works and where are the forcing and where are the feedbacks and ticking points. And if carbon dioxide go to the ocean, what happens with the ocean? This is like that there is that carbon dioxide could be dissolved in water to some extent, and you probably, maybe you can remember this from your primary school. And what happens in the ocean? What is the answer of the ocean? As you can see, with the different scenario, we achieve different prediction. We already know that we have some issue in the ocean already. Some very beautiful features of the ocean disappear. But I would like to draw your attention what means, let's say, natural acidification. Actually, it's not acidification, it's more based as far as pH, as you can see, and very small change. I would like to draw attention to this, that in the worst scenario the pH will change only slightly, 0.4, and this could cause a very huge change in our living in the ocean. It means that we lost biodiversity in the ocean. We observed now very small changes, and we observe huge losses of biodiversity. And this is even more difficult to understand, because we have these carbon sinks. Within these carbon sinks, I've told you that majority stays in the atmosphere, majority of carbon stays in the atmosphere, and this carbon dioxide which stays in the atmosphere, of course, rise the concentration of this gas, and of course stop releasing, reflecting of the energy from our planet. And this unbalanced, we used to say that this is unbalanced forcing, which means radioactive forcing. It means that we have more energy, and this energy is gathered on our Earth. That's why we are telling that this is greenhouse gas effect, that our Earth is start to boil because we achieve more. We achieve the same amount of energy because the sun has always the same amount of energy which reach our Earth, but we're reflecting less. It means that more energy stays with us. And here you have also this scenario which are showing us how much energy will stay with us if we increase the concentration of carbon dioxide in our atmosphere. So here we have this data given by this. It's very important to understand that if we will have more greenhouse gases in our atmosphere, we will keep more energy on our Earth. This energy will be not reflected and stays with us. Paradoxically, we can say that these aerosols, and this is very important to understand actually what is the aerosol. Aerosol is the particulate matter which we release during, for example, carbon burning, carbon incineration. Aerosols are emitted by industry and also in volcanic eruption. As I've mentioned you at the very beginning, that due to volcanic eruption, the temperature was down around 3 to 4 degrees because volcanoes, when they erupt, they release, of course, a lot of carbon dioxide, some methane, and other gases which could be very, very dangerous, but they are also release a lot of aerosols connected with the sulfur, and this stop the sun radiation which reach the Earth. So in one hand, the volcanic eruption caused the greenhouse gas effect, but of course, in the same moment, it mitigates by releasing aerosols, and paradoxically, volcanic eruption is not actually the forcing of the climate change. Not now. Maybe during the historical geological period, maybe it worked like that, but from now, our planet is a bit, let's say, more quiet than it was in the past, and that's why it's not now not any longer the force of climate change. In this, what we can sometimes read in this paper, that volcano eruption caused the climate change now. So it is false. And from this, that we achieve more energy, means we achieve the same energy, but more energy stays with us. It's very important to understand where this energy goes to. And this energy goes to the ocean, in majority, as you can see. The energy goes to the ocean, and it means some consequences to the ocean. Part of this energy goes to melting ice. Only 5% go to the soil, because soil has no capacity, and the less energy goes to the atmosphere, as you can see. Why so big energy goes to the ocean? Maybe you know the answer. Is somebody know the answer? Why so big amount of energy go to the ocean? Don't hesitate to tell if somebody knows. Okay, this is connected with the thermal absorption of water, which is actually unlimited. So water could absorb a lot of energy, as we can, for example, boiling water for the tea. So the temperature is 100 degrees. So a lot of energy water could take. And of course, this has some consequences because part of the water became a steam, which has also a consequences for climate, our climate, because this steam is also a gas which could increase greenhouse gas effect. And as a consequence of this, that ocean absorb over 90% of energy, the water temperature increase, especially close to the surface. What means that, for example, the ice is melting. When we have ice on water, then the ice is melting, or it's not regenerated, the ice. And here we come back to the albedo. If we do not have ice cover on the ocean, we again trap even more energy from the sun, because the energy is not reflected from white cover of snow. So this is a feedback. This is a feedback which could cause again the, let's say, self-running process, like in the cycle. So this is very important to understand that the changing of albedo due to absorption of energy could accelerate the process of boiling of our planet. Again, hotter ocean and a hotter atmosphere lead to stronger evapotranspiration. And it was calculated that for 1 Celsius degree higher temperature, we have the 7% capacity, bigger capacity in atmosphere for the water. It means that if we change the temperature for 2 Celsius degree, we can evapotranspirate 14% of water more into the atmosphere. And it means that hotter land and hotter atmosphere leads to stronger evapotranspiration, and this causes, of course, dry of the ground and formulating of the clouds, and this causes extreme events. And here I would like to come back to your memory about what happens in actually our part of Europe in September, when we have very huge precipitation, which was generated in the Adriatic Sea, because this peninsula, I mean Italy, get a lot of warm, very hot weather. The temperature was extremely warm. The Adriatic Sea and Mediterranean Sea was very, very, very warm. And then this huge amount of water evapotranspirated in the form of clouds was pushed, as it is usually it's pushed during this part of the year, was pushed to the north when meet the mountains, and then precipitate on our part of Europe and cause a big floods in Poland, in Czech, partly in German. So this actually was caused by such phenomena. And here some consequences. This is the second part of my presentation. Some consequences of climate change, global, regional impact. Let me start with global. As you can see, many direct and indirect consequences of climate change. Losses of terrestrial and marine biodiversity, river flooding, cyclones. This is very important to understand that when the ocean is warmer, the cyclones are even more dangerous than usual. They happened more frequent. They happened in such places which never happened before. Then we have a lot of droughts. Then we have marine submersion, because we even do not touch the what happens if the Greenland, for example, will melt. It is estimated that around that the sea level rise up to 7 meters. We already observed that we have some new diseases. We could have some new, let's say, new, for example, mosquitoes and others which we never have in Europe, for example. Of course, decline in agriculture yield. This happens already. Some farmers needs to change the crops, because they are not able to produce the crops which they produced 20 years ago. And finally, we could have refugees, what actually happens already, and conflict for resources as usual. When resources are limited, people are start to fight. Very important is to understand that we assume that the climate change is linear, and this is really forced. That this assumption that relationship between temperature rise and association phenomena like ice melting or sea level is not linear. It's not linear, and very difficult is to set up the tipping points, because in many phenomena we are not able to set up the fitting point. So this assumption that every additional 1 degree of warming will result in some a bit greater impact, it's really something which is false. And here you have a data, as you can see, showing us this how fast we are crossing different boundaries, planetary boundaries. Now they are determined that we have 9 planetary boundaries, and as you can see, in 2009 we cross this red one, orange. We cross 9 boundaries. In 2015 we cross 4, and in 2023 we cross 6 boundaries already. And let's have a look a bit closer to those what we have here. So we assume that in green we are in safe operation. So we are in safe operation with the ocean acidification, atmospheric aerosols. We do a lot to decrease atmospheric aerosols, and we are quite happy because we mitigate these particulate matters. Probably majority of you knows about this much better than I do. We do a lot with this stratospheric ozone depletion. Many years it was said that we have an issue with ozone depletions, but we hopefully could stop it. What we actually failed to do is, for example, novel pollution, novel entities which we release to the atmosphere, to the water. Actually, such entities are, for example, PFASs, which we are now forced to measure in drinking water, and other even undefined type of pollutions. We just call them new emerging pollutions or persistent organic pollutions, because we actually do not know what happens with them and how they will act. I would like to show you, of course, that the climate change, what we have, this radioactive forcing, which is actually on the limit. As you can see, we have high risk concentration of carbon dioxide. we have an issue with biosphere integrity because we have a lot of disaster with our genetic. We manipulate a lot of with genetic, and it means that we have an issue here. And of course, we have the so-called biochemical flows with nitrogen and phosphorus. We release too much nitrogen and too much phosphorus, as you can see, which cause the eutrophisation. And then eutrophisation is a kind of feedback of the ecosystem with unknown, let's say, tipping point, because it leads us to the degradation of the water bodies. So situation is not so nice, and the consequences for the region, for me, it was the most easier was to find the consequences for Poland. And here I would like to show you the average number with the dates with the temperature over 30 degrees, as you can see here. And here is the rise of the number. Here you have a date when it was 50 years ago, let's say 20 years, even less than 20. And here we have last decade. So you can observe that even in relatively small area as Poland is, we can face this average date with the temperature over 30 degrees, which is, I would say, quite difficult in our latitude, because we are not used to such temperature. Could be even, as you can see, even more than 14 or 80 days in this central part of Poland. So people need to get used, and of course it's very difficult for children, for older people to stay in the cities, to have a rest, to sleep during the night, because the consequences is also very high temperature during the night. So these are the consequences. Again, the situation for the last year, where even in Poland, you can see here that here we have the precipitation 5 millimeters of precipitation for the 15 days, which is actually nothing, these 5 millimeters. And southeast part of Poland achieved huge amount of water, because in Poland average precipitation is around 600 millimeters. So this is that we achieve in 50 days half of the year precipitation, which is actually very huge amount of water. So from one side of Poland, as a consequence of climate change, we will have floods, and in another part we have droughts. And even worse situation, which was announced, as you can see in this year, as a consequence of this graph, and most likely consequence of this graph, that this is the number of the station when we measure the flow in the river below average. And here you have the number. Let's have a look, for example, for this, let's say pink one. Let's say pink one, because you are able, oh, maybe green. Maybe green is also good. Here, the green one starts with 100, yeah. And as you can observe here, 10 years ago, maximum it was noticed for 200 such stations all over the Poland, where the flow in the river was low. Last 2 years, as you can observe, last 2 years it was already almost 400, and as a consequence, we can notice that in the last day of January in this year, our Institute of Meteorology and Water Management announced the consequence that the soil moisture is very low, and in the consequence, we have a lot of hydrological threats in Poland. As you can see here, this red means that there is no water underground. The resources are very poor. So these are the consequences of climate change. Coming a bit closer in our region, as you can see here, for consequences for example, water management in the cities. Usually we, for example, design stormwater network or wastewater network for the phenomena which are called 100-year phenomena. It means that such which could happen only once per 100 years. But as you see from this, we have a lot of such phenomena in Poland, in Gdańsk, especially in Gdańsk region. We already have this phenomena of 100 probability 4 times in this century. It means that for these 25 years we have already 5 phenomena which could happen only 1 per 100 years. So these, of course, are the consequences for the cities, for the management. In this moment, I would like to cite this, what is in Intergovernmental Panel for Climate Change, that every action matters, every bit of warming matters, every year matters, and every choice matters. And here, bad news is that we shouldn't look for other countries. We should, as a Europe, we should look for ours, because as you can see here, the 50% of the poorest people release only 10% of consumption and emission from this consumption, and majority of people, which unfortunately we are in Europe the richest, we consume and release around almost 50% of this what is released to the atmosphere as far as carbon due to our activities. And as it was said, individual actions matters. So our personal choices to reduce our contribution, it means mitigation to climate change. We can divide it into low impact, moderate impact, and high impact with the release. And as you can see here, even matters how we use, for example, how we wash our clothes, how we can replace a typical car with the hybrid, how we dry our clothes, of course, what we eat and how we behave, with our everyday and not only everyday activities. So this is very important to understand that food contributes to greenhouse emissions and across to supply chain. That's why it's becoming more and more popular to eat the food only which was grown, let's say, nearby. That's why, for example, avocado is the more unenvironmental friendly in our latitude vegetable, because this is a monoculture, which means that we deforestate, then we use a lot of energy to grow, and then we use a lot of energy to transport. And here you can observe, for example, that then beef is also quite environmental friendly food for human, because there is a huge land use, then is a farm, which is a huge release of carbon dioxide and greenhouse gas emissions, and then we have transport and other. From this perspective, as you can see, citrus fruits, apples, root vegetables, even banana or nuts are not so bad as you can see. And this is actually the end of my presentation. I am wondering in which moment we are. So maybe you could tell me in which moment we are. Climate change timeline. Climate change is not real. Okay, climate change is real. We are just not convinced it's caused by human, means the orange. Then we have oops, and then we have. Okay, thank you very much for your attention.